materials. Before going into it, I'm going to briefly. I'm going to flash these references, and given the fact that the talk is recorded, you can find them if you don't manage to copy in time. And first explaining the words in the titles, and I'm not explaining them myself, but let people explain who know much better than I do about the meaning of these words. So what are quantum materials? Let the person define who maybe has synthesized most of them of cover. The simplest of definitions is that a quantum material is one whose electronic or magnetic properties are best described as having a non-trivial quantum mechanical origin. That's a negative definition. And now I'll let somebody explain topological order, who invented it. And again, we get a negative definition. So Xiaogang Wen says in the above discussion in this paper, I only refer to topological order by what it is not, symmetry breaking order. So we have two things that are negatively defined. Xiaogang Wen goes actually further and says that particular characteristics of topological order is that they are long-range entanglement. This entanglement is very important. And the goal of this talk is actually I'm going to give you toy models where topological order is very well exemplified. And then I'm trying to make a connection to quantum materials, depending on how much time we will have. Good. So this is motivation by examples in terms of materials or physical systems. I guess the historically most important part was the systems which launched the story of topological order is fraction quantum Hall effect. So what you see here is Hall resistance versus magnetic field, and you see all of these fraction quantum Hall plateaus. I will not speak about this at all. Something that attracted a lot of interest in the past few years are quantum spin liquid candidates. So this is ruthenium trichloride, which has a putative regime with a quantized thermal Hall conductance, which is attributed to a quantum spin liquid state. It's very much on a debate, but I guess it's a fair candidate material, and it's a hot topic. This is a little bit closer to what I'm going to speak about, because I'm actually going to present a Toric code, which is can be seen as a quantum spin liquid. Another aspect which I hope to cover in the second part of the talk is the question about Fermi surface reconstruction. So these are strongly interacting metals. So this is a cuprate, which upon doping, actually in a sufficiently strong field to suppress superconducting order, seems to display a jump in the Hall number without any Fermi surface, without any symmetry being changed from one side to the other. So this would be an idea of Fermi surface reconstruction without symmetry breaking. And this is actually something that's surprising, given Laplace theorem. I'll go through this. So one way to explain this is something related to topological order. And on the right, you see actually a heavy fermion material, which also within a phase of a given symmetry. This is within a phase with a given broken symmetry, but both left and right of this B star here, it's claimed that the symmetry is the same, and at the same time, the Hall resistivity jumps in a way that could be associated to Fermi surface reconstruction without symmetry breaking. This is more in materials, and outside of solid state, there is actually an interest in topological order as the topological quantum error correction code. So what you see here is the Sycamore chip by Google, and in fact, the Toric code was sort of the first experiments which are going to implementation of the Toric code have actually already been done on this or similar systems. And finally, this is a bit academic, but actually topological order has, if you're a purist, has actually been observed experimentally first when superconductivity was observed, because superconductivity can be understood as a form of topological order, given the fact that you cannot break a local gauge symmetry. Okay, so this is motivation by examples, and this is the outline. So I'll go through the Toric code and explain this model, which is the simplest model of topological order. And then I'll couple fermions to it, and let's see how far we can. Okay, so the Toric code is essentially a model which is a Hamiltonian describing interacting spins. The spins are located on the links of this square lattice. So there is a spin 1/2 on each of these squares here. And the Hamiltonian describing the Toric code is given by these two terms here. So it's a sum over all plaquettes. And then there is this plaquette operator here, and then a sum over all positions or stars. Then there is this star operator. And each of these operators that are summed over is by itself a product of 4 operators. So the product of 4 operators corresponding to 4 different spins. For example, for the plaquette, it's the product of all sigma z's. And for the star, it's the product of all sigma x. So plaquette is around a plaquette, and the star is around a certain vertex. Yeah? So sigma x times sigma x times sigma x times sigma x. Okay. And this model is particularly interesting because it is soluble. And the reason for this is actually that there is a macroscopic number of integrals of motion. So it turns out that all of these B's and all of these Q's commute with each other. And by consequence, they all commute with the Hamiltonian. And as such, if you know the Eigen States of all of these B's, it means that you know an Eigen State system. So how do you see actually that these Q's and B's are conserved? So clearly, all Q's commute with each other because they only involve sigma x's. So all sigma x's commute with each other. All B's commute with each other because it only involves all sigma z's. B's and Q's which don't touch each other clearly also commute with each other because they live in separate Hilbert spaces. The last thing that you have to ask yourself is what happens when a Q, let's say this vertex here, is overlapping with a B. How come these two commute with each other? And the reason is that there are 2 Pauli matrices, let's say 2 sigma x's from the Q's and 2 sigma z's from the B. And as you commute one operator across the other, you acquire twice a minus sign, which then gives you a plus sign. And then this means that actually all Q's and all B's commute with each other. The other piece of information that is important is that the Q's, as they're just, and B's, as they're just product of Paulis, they square to 1. As a consequence, their eigenvalues are plus or minus 1. So essentially, this is now, I will go into more details, but essentially, the number of integrals of motion is the same as the number of degrees of freedom that you have, up to a small subtlety. So, so indeed, you have 2 spins per unit cell, right? There are 2 links in a given unit cell, and you have these 2 operators per unit cell, 1 Q and 1 P. So this is enough to describe any state. So any state is given by the set of all Q's, their eigenvalues, which can be plus or minus 1, and all B's, which can all be plus or minus 1. Now let's assume that K and H are both positive. So then the ground state is going to be the situation when all the Q's are in a state which is plus 1, and all the B's are in a state which is plus 1. Okay, so how can we draw such a state? Let's start with forgetting about this term here with the Q's for the moment, and we just take the B's. How do we make this state happy? We want to have a product of all sigma z's being plus 1, given that K is positive, so minus K in front here. So this is one way of getting this. Just put all spins in up position. Then it's a product of all plus 1s, and in the end you get each plaquette, you have an eigenvalue plus 1. Now, of course, there are various ways of creating such states which have all plaquettes being plus 1. And in fact, this term here is going to split the degeneracy of all possible states. And the way you do it is you just try to make all of these Q terms happy. You just introduce a projector which projects this state here onto a state which makes all Q terms. So the state by itself is not an eigenstate with respect to this Q operator. If you just project it, as I said, Q squares to 1. So if I apply Q to this here, I get Q plus Q squared, which is 1. I just get the same thing back. And for the B's, let's act with the whole Hamiltonian on this here. All the B's commute with this projector, so I can bring any B across here, and then we'll act onto this one, and the B's are designed to give all B's. Okay, so this is actually the ground state of the system. I will go into more details about the ground states, but this is lowest energy state. And actually it can be expanded, and you will see immediately where this entanglement comes from. So this is a product of all of these projectors, but a product which, if you like expand it, there will be macroscopically many terms in the sun. And I just drew the first few of them. So if you have, for example, here this product of all ones, it just leaves this term here, this state invariant, this is the state. And then there is, for example, a state where you have one Q acting on this, as you expand this product. This will flip, a given Q will flip 4 spins from up to down. It's represented by these 4 spins, for example. And of course, there are all possibilities of having 4 spins split somewhere. And then you act maybe with 2 Qs, then this one maybe its neighbor, and you see there are like this little loop of spins. In fact, actually, you can just draw the loops, which are loops of flipped spin on top of this all up state. And in fact, this leads to this notion of string nets that is present in this topological order community. But the main statement that I wanted to make is that you see it's a superposition of macroscopically many states. And if you think of the simplest example of an entangled state that you know, I guess a singlet, right? You have 2 spins and you have as many terms in your sum as you have degrees of freedom. Up, down, and so on. Here you have essentially as many terms in your sum as you have degrees of freedom, but it's macroscopically many.
So in the typical configuration in that sum there, the string nets are infinite, they're percolating, or
so you have all possibilities, actually with the same weight, all possibilities of having closed loops. And that's it. Yeah. So you can have I'm not sure what you mean by percolating. There could be in principle, so first of all I have to ask the question what about boundaries. I guess you want to know whether the string goes across or not, right? And that actually, okay, so now it's a question about what are your boundary conditions, and ultimately it will bring me back to the question about the ground state determinacy, whether there are strings which are going across or not, across the whole system or not, right? Whether it's an even or an odd number of them.
If I just took a random one of those somewhere in the middle, would it be a pretty good representation of the whole sum?
What is a good representation? What would I think of as a good representation?
Just, the Eigen state is clearly the sum of all of them.
Right, exactly.
So if I took a random one somewhere in the middle, would it be close to the Eigen state?
Well, in the sense that, so if you take an overlap, it's going to be 1 over n. Right? Yes. So, and at the same time, a given state actually breaks symmetries. For example, this starting state, it breaks the spin symmetry.
I was just thinking like a BCS state.
Yes.
Doesn't have a definite particle number, but it's a very good representation of an Eigen state with a definite particle number. So in a similar way, could I take a typical state and this doesn't have a well-defined Q equal to 1 on each side, right? Does it somehow close to the ground state, or is it still quite far? So I really have to insist on every single one being there to get a pretty good representation. You can just a question. Questions.
Yeah, I don't have a good question, but answer. But I think an important bit is that this is a ground state which does not break any symmetry, and that's only after you pick the sum of all these. Given state will actually break the symmetry, and given the fact that not breaking a symmetry is a important characteristic for a spin liquid, I'm not happy to look at just one state, right? And also entanglement is something that simply appears because it's the sum of, right? Not just a product state. The given state will always be a product state. So I think in that, at least in these aspects, I think you cannot get with a single representative. Could take 2.
Quite a few.
Yeah.
So what do you mean by condensation?
Okay, yeah. So this is actually a word that appears. I think it just means proliferation of all of these, all configurations.
You mean like strings
but
with
it's
like
not,
arbitrary length?
Yes, they're all arbitrary lengths and all possible configurations that are summed up to the same way. Okay. Now excitations. So far we spoke about the ground state only. So this, as I said, the Eigen states are given by the sum of the configuration of all Q's and all of these B's. So the simplest excitation that you can have is you flip one of the B's or one of the Q's. And here I flip one of the B's. Flipping a B costs you an energy of 2k, because instead of having minus k, you have plus k. And what you want to have is you want to have one plaquette, which is B equals -1. That means one plaquette has an odd number of downspins. But you want to have all the other plaquettes still having an even number of downspins, such that the B's are going to be +1. So that means that there is actually, if you try to flip one plaquette, you have to have a string which goes out all the way to infinity of, let's say, 2 downwards pointing green arrows. So, okay. But at the same time, you have this local, this is a local excitation. That's why people will speak about this as a particle. I will go to this in a moment. And in fact, this particle is, since it's flipping, these plaquette terms are called flux terms, and it's the standard language of calling this an M particle, standing for magnetic. On a system with, let's say, periodic boundary conditions, such an M particle does not appear alone. We have actually a second one, because the string has to start somewhere and has to end somewhere. So you have actually two such particles, two such plaquettes which are flipped. And the important bit about it is that these two particles essentially live their own life separately. So the energy does not depend on the length of this string. I think even I have an animation for this. Yes. So you change the length of the string, take a different type of string, the energy is completely independent. The energy is just twice the energy by each of the ends. String. As such, they live really like the word is deconfined particles live their own lives. And the word deconfinement is the one that you know from QCD, where in QCD you ask yourself the question, okay, can I have two quarks and pull them apart and let them live their own life? And the answer is no, because the non-abelian nature of the gauge group is such that you will always get color neutral objects. But here the situation is different. You have two of these M particles which can live their own lives separately, and essentially they're just particles. Okay, and I introduced this string, which is called WM, because it's a string of sigma x's along the dual lattice. And of course, you can do the reverse thing also. You can also study, by the way, I'm dropping all of the background from now on, just to draw less. And you can do the reverse. You can actually flip two Q's, let's say here and here. And flipping two Q's implies that you have actually a string of sigma z's going along the actual lattice. But otherwise, this is actually completely dual to this. Yes.
After the projection, is there any meaning to the actual path of the string?
Yes. Okay. This is actually very important. That there is a projection, that there is still a sum of all possible loops, which means that essentially you already have a superposition of all possible strings, right? Because you can add a loop here, for example, which is anyways already accounted for in the sum of all the loops. So this is very important to keep in mind, that I'm only showing a representative state, but there is actually a superposition of all of those, and that's actually also the reason why it doesn't really matter which of these loops and strings I'm presenting. Okay, so we have these two excitations, which are sort of local, called M and E particle. E stands for electric. And now I'm going to speak about exchange statistics. So these guys are actually anyons in some way, or at least they're leading to some anyons. And I have to remind you of exchange statistics, I guess. Yeah? So the situation is as follows. If you have identical particles, you have a wave function which depends on position R1 and R2. And at least for the situation of abelian anyons that we're discussing here, the wave function acquires, it's allowed, since the particles are indistinguishable, the wave function is only allowed to acquire a phase as it exchanges the position of two indistinguishable particles. This is a phase, let's say e to the I. And then you can ask the question, what happens if I do it twice? Well, obviously I come essentially back to something which looks like what I started from. It's e to the I2 theta. And you can ask yourself the question, okay, so what actually happened? In 3 dimensions, nothing happened, because exchanging twice means that here my right hand just goes around the left hand. That just means that from the position of perspective of this one, just have a loop of my right hand going around my left. So this particle just went around it. And in 3 dimensions, I can actually undo this loop. That means that e to the I2 theta has to be 1. Such that theta has to be either 0 or pi, and these are the options called fermion or boson. In 2 dimensions, the situation is different because I cannot undo my loop. Once I've gone around a point, I cannot just contract it. That's why we have anyons in 2 dimensions. But it turns out that actually, if you have a boson, if you have an m particle, it behaves like a boson to itself. I just want to change the position of this m with this one, just flip around the whole string, and I don't get a phase at all to my wave function. So actually, there is this representation for this here. If I have 2 m particles and I exchange their position in time, it is doing nothing to the wave function, which means that it's just the same as switching their position is the same as just leaving them where they are. And the same is true for 2 e particles. However, you can ask the question also, what is the mutual exchange statistics, or statistics of braiding one particle around the other, bringing one particle across. And there actually something interesting happens, because let's now ask the question, what happens if I bring an E around this M here, for example. I cannot just exchange the position. These are distinguishable particles. So this doesn't make sense to compare a state where I have an E particle here and M here and the reverse situation. But what I can do is I can just ask the question, what happens when I bring the E all around? And that's represented like, this doesn't make sense, but this does make sense. I just bring the E back to where I started from. And what happens is that I bring this E particle all the way around here, and I will intersect this loop, this line here, this green string, exactly once. At which point I will acquire a phase of minus pi, because there is one sigma z which is going to be commuting with the sigma x, and I get a minus sign. So it turns out that bringing an E across an M gives me a minus sign on the x. This is called that they are mutual semions, E and M.
So how do we prove that the self-statistics of these particles goes on? So I understand that like the main reason might be that simply they are created by the same sort of like string operators, right? And that whenever you intersect, you don't pick up any phase. But like still, like I've just seen some arguments which are like pretty like involved and involve like certain machinery from like I don't know, topological quantum theory. But I'm wondering whether there's like a very simple way of just seeing that.
I think here it's just this is why I'm presenting it. It's a toy model where you just do step by step by step, and you just take this string here and you just bring it across to the opposite direction, and you don't acquire any phase at all. And actually, by the same token, you can do this operation. You do see that at some point you will get extra cut this sort of branch cut string, and we'll get a minus. I guess in general it's a non-trivial question. Okay, so now I'm going to speak about which other excitations there can be. And that's a question about fusion rules. So what happens when you bring 2 anyons close to each other? This is, I think of it the same way as I think of 2 spins which are bring close to each other, and I want to know how they behave as a whole. And 2 spins, if I bring them close to each other, they behave either like a singlet or like a triplet. And you can ask the same question here. If you bring like 2 m particles close to each other, how do they behave as a whole? If you zoom out, essentially, if you just bring this m here on top of this one, it will behave like nothing. That's represented by this 1 here, which means the ground state vacuum. So we're trying to ask now the question, taking these excitations, if I have 2 of them, what happens if I bring them close to each other and zoom out? 2 m's, bring them close to each other and zoom out, I just get vacuum, same with 2 e's. But the important thing is that you can also ask the question, what happens when I bring an e and an m close to each other? How do they behave? And that's actually something else. It's not vacuum, it's not m, it's not e, so it's something new that we call epsilon. Sort of the bound state of this e and m there, that's the new characteristic. And epsilon by itself, you can ask yourself the question, what happens if I bring other anyons close to it, and for example, bring in another m, will remove this m and I get an e, And so on. Bring another E, M, and two epsilons together just fuse to the vacuum. Okay, so I did this to just motivate that there is another sort of anion that we discuss the exchange statistics here. I should also briefly mention that all of these anions, they're corresponding to sort of so-called super selection sectors, which are states which you cannot mathematically transform one into the other. But the main point is I wanted to also briefly discuss what happens if I exchange two of those bound states, two of those epsilons. And now these are indistinguishable particles, so I can just exchange their position. And we can use these equations to prove what happens here. So you see, I bring these two epsilons across each other. There is this epsilon, which is here, there is an intersection between blue and blue, which is this one. So I can just undo this crossing here. So here I've undone it, and I just go up here and up here. And similarly, I can do it on the right. So there is a crossing of two greens. I use this here. Without acquiring a sign, I can just undo this crossing up. And I'm just left with this M going all around this. But I've already learned that this is giving me a minus sign. So ultimately, I get that minus sign here, and these two all lines go straight up. So exchanging the position of two E's gives me a minus sign on the ground state, which means that they behave like fermions. And to me, this is the most fascinating part about this model. So you start with a model which is just qubits, let them interact, with just spins, and suddenly you have a fermion which comes out of it.
So one question: if you, I mean, the M's are defined on the plaquette and the E's on the vertices.
Yes.
So once you define this composite object, I mean, there are four corners of the plaquette you can choose, and if you then merge two epsilons, isn't there some ambiguity?
Well,
you
can definitely bring them directly on top of each other, right? But of course, you're right. There are like four possibilities of, let's say, I fix the position of the E and give this, and then I have four possibilities of having the M close to it. But if I bring another one, which is looking, let's say, I don't know, northeast instead of northwest, I can of course rotate it and just get rid of it at no cost. But in principle, you're right. It looks as if it had some direction. And by the way, this is also related to the question of why does it get a minus sign if I just put those two strings just parallel to each other. If I rotate the whole thing, I suddenly have, so I start maybe with green on top of blue, but then I rotate it and I end up with blue on top of green, and actually bringing it back down this moment where you would get the minus sign. Okay, so
sorry, just on this. So maybe two questions. So you cannot move if you want to have this epsilon particle, you cannot suppose like I moved like one of the E's to be like very far away. Like, do you still have a notion of like this bound state thing?
Just or you want to bring this E away, or you want
no. So the you have an M and E, and instead of like fixing like shifting it by like I don't know half of the like lattice vector, I'm simply like shifting it by like some arbitrary amount, and then like moving them all together always and treating them as one particle. Would that still be this epsilon?
So I was sort of a bit blocking, just saying I zoom out, but zooming out actually refers to, so there's a notion of a scale that I have in mind when I say zoom out. And it turns out that actually, strictly speaking, topological order appears in gap systems. Right? Actually, there is a, so I saw a talk by Nick where he says definition of topological order is the gap system. Of course, it allows for trivial, but but the important bit, since there is a gap, there is a scale, and you can sort of at least ask the question within a given, within the scale, and a length scale, which just makes sense.
But the M and E are not bound to each other, right?
They're not necessarily bound to each other, but you can of course ask the question: what happens if I allow for interaction that do bind them to each other? In principle, you can go beyond the Hamiltonian and let them bind really, right?
I see.
So far, I mean, at this point, there is no need to do what I'm doing, right? Because it's just excitations which happen to be close to each other.
And is there a known deformation of the toric code that does bind?
I think there are, I think there are such deformations where people just bind these two together. Okay. Yeah. Good. So I have 15 minutes left. So maybe I do tell you something about this Fermi surface reconstruction. and just completely jump from here to the situation. So I don't tell you about, and we can discuss this later. I don't tell you about the ground state degeneracy, but maybe I should tell you briefly that the existence of these anions implies that on a torus, there is a ground state degeneracy, which is, in this case, fourfold. So this is the two topological. Okay. And instead, I'm going to speak now about toric code with fermions. So I'm extending this model to a model which has toric code plus fermions. And fermions which are hopping around on this lattice, but each time they hop, they feel, so they measure the z projection of the spin on a given unit. And at the same time, there's a little bit a different definition for this Q operator, which is not only anymore the product of all sigma x's, but contains the fermionic parity on this side. So importantly, still the B's and Q's all commute with each other for the same reason that I explained before. But also all the B's and all the Q's commute with the fermionic term here, the term of fermionic hopping. The reason for the B's is trivial because it's just sigma z's. For the Q's, you see a Q acquires a minus sign, let's say a Q, which is a star operator, which is here, will acquire a minus sign because there is a sigma x, which anticommutes with the sigma z on this bond here. But at the same time, there is this -1 to the n, which is measuring the fermionic parity, which is going to acquire an extra minus sign because the creation operator at the site here is changing the fermionic parity by, goes from -1 to +1. So again, because of two minus signs, the Q commutes with all of the fermionic hopping terms, and therefore actually is an integral of motion. So we have at least, we know that all the B's and Q's are conserved. We can at least find the ground state in the limit where K is much larger than W. I can explain later in more detail what happens if K less than W. Okay, still there is a macroscopic number of integrals of motion. And what we can do is we can try to find the ground state. So the state there is a Hilbert space, which is all of these sigmas, and there's a Hilbert space, which is referring to the fermions, so it's a product. Let's say K is positive and large. Then what we want to do is we want to get into a toric code ground state. Essentially, we want to do first at h equals 0, all the B's point up, all the sigmas point up, all the B's have expectation value 1, which corresponds to 0 flux. So this here is essentially the same tri-state that we had before. All arrows point up here on the links in the sigma when the K is the largest energy scale. Once you have fixed all the sigmas pointing up, this is just a triple hopping Hamiltonian in terms of C's. This is just a state which is giving you some kind of large Fermi surface. And then what we're doing again is we're projecting this with all the Q's to make the Q partner. So again, if you just look at this Hamiltonian here, if you act with the Hamiltonian onto this here, you see, so the Q is happy anyways because it's the projector. The B commutes through here, so it acts on here, and we make each of the B's happy. And then the fermionic hopping term here will pass through here, because so the Q's, all the Q's are actually commuting with this fermionic hopping term. Then we evaluate the sigmas, and then we have just the fermionic hopping term on the lattice where we have +1. Okay. But the situation is different if K is large and negative. Yes.
Does this not depend on the size of H relative to?
It does not actually depend on the size of H. Yeah. So let me just. You see, they all commute, so I think that's the important bit, right? I can tell you maybe why it depends on the size of K, because so anyways, you think that all of these, as I said, so all the B's and all the Q's are anyways conserved, right? So you can just define the state by fixing all the B's and Q's. Yeah. Of course, if it's a random configuration, it's hard to solve the fermionic problem. And the reason why it depends on this ratio of K over W is that the fermionic term by itself, imagine there is no K at all. The fermionic term by itself prefers to have, depending on the filling that you have, prefers a certain flux. Flux wants to be something like 2 pi times 10. And that means that actually you have to ask the question whether when this one is stronger than that one and you're at half filling, then independently on the sign of K, this wants to have flux pi. But for the H term, it doesn't.
Does the fermionic term commute with H?
Yes, yes. So the Q part commutes with the hopping because there is 2 minus signs, one from sigma x and one from this fermionic parity.
Okay.
Yeah. Okay, so when K is negative and large, turns out that we want to have flux pi, so that means that all the B's want to be -1 on each of these brackets. Other than that, you can essentially continue the same. So you start with the trial state, you have flux pi state. One trial state is, for example, that you have all spins pointing up on black bonds and spins pointing down on blue bonds. This gives you a product of all spins being around the plaquette is going to be -1 because there's 1/5 spin. Okay, so this is your trial state. In the presence of such a trial state, you can solve the fermionic problem. It gives you something that has Dirac nodes. And you make the H term happy with this plaquette. And as Sam just asked, when you're in the regime when W is smallest compared to K, you will have actually some states, which I don't want to get into details, but these states essentially are just determined by the filling of fermionic sector. While these states here, as long as K is sufficiently large, are independent on the filling. Just will shift up and down your Fermi surface. Okay. But the important observation is that we have these 2 states are the ones that I want to briefly concentrate for the last 5 minutes. So this is actually the phase diagram as a function of this K over W. As I said, when it's large in absolute value, we will be in some phases which are independent on all the other parameters. This is this one with the large Fermi surface. It's called actually orthogonal. I will probably not have time to explain it, but it's essentially a metal with a large Fermi surface. And it has flux 0 through each of the plaquettes. And here there is in the yellow area, there is a state which has Dirac points and a small Fermi surface. And importantly, okay, there are some states in between that I don't speak about. This is some transition in between. But importantly, these 2 states, yellow and blue, neither of them breaks any symmetry. And at the same time, they have a small Fermi surface or a large. Turns out that these 2 states are actually, I said they don't break any symmetries, but they're characterized by a different form of topological order. So they're both Z2 topological order, but they have different representation of translational symmetry. It turns out that because spontaneously the system wants to have this flux pi for each of these plaquettes, the translation, so it's translation in X and Y direction, they actually follow the so-called magnetic translation algebra, which we know from 1 levels. So it's actually, despite the fact that no symmetry is broken, these states can be distinguished on this formal way and lead to this different size of Fermi surface. Now, I was going to say briefly, so I will not explain in detail how to get to this unless you ask me later. But I was trying to argue that, well, this has, at least conceptually, gives you an idea how to circumvent Lattimer's theorem. So Lattimer's theorem tells you that the size of the Fermi surface is given by the density of fermions independently on the strength of interaction. And at the same time, here, and actually an important ingredient for Lattimer's theorem is that you don't break any symmetry. Obviously, if you have an antiferromagnet, you will get your burn zone falls down, and you can have a smaller Fermi surface in the case of symmetry being preserved. Here we have two states which have different type of topological order, and it turns out that this different type of topological order actually allows you for having these different types of sizes of Fermi surface. And the reason, very briefly, is the following. One way of deriving Lagrange's theorem is involving a momentum balance argument. So what you imagine is, I have slides for this if you want to ask me more details, but you imagine that you put your system onto a cylinder and you ramp a flux through the cylinder. And actually what you do is, at some time at infinity, the flux is 0, and then you go at plus infinity, it's going to be flux 2 pi. Before and after you have ramped this flux, the system, so at time equals minus infinity and plus infinity, the system is gauge equivalent by means of a large gauge transformation. Flux 2 pi is the same as infinity is nothing. The spectrum has gone back to itself, but the wave functions might have shuffled. And it turns out that actually ramping this flux, the moment that you increase the flux, you actually do have a non-trivial electromagnetic field. And you start to spin the system. There's an electromotive force which starts to spin the cylinder. That is a way of, you can define this angular momentum, or the momentum in the direction of your system, as being a momentum that has been transferred to the system during this process. This is one way of counting the momentum. And another way of counting the momentum is microscopically. You ask yourself the question, which excitations, low energy excitations in your system are carrying this momentum? And in the usual ways, you say, oh, these are quasi-particles close to the Fermi surface. And then you can actually count how much momentum these quasi-particles are actually carrying. And since I said this is close to the Fermi surface, there is, just by balancing these two types of counting the momentum, you find that the size of the Fermi surface is actually given by the density. Here we have a loophole because we have topological order. And as I explained before, there are these anyons around. In this case, it's this M particle. What you're doing is essentially you're ramping your flux, but there is another sink for the momentum that you have given to your system. And this sink is this M particle. And therefore you can actually find another way of balancing this momenta. You don't necessarily need to require that the quasi-particles are going to carry this momentum. And thereby you can circumvent the necessity of a large Fermi surface at, let's say, filling a half. So this allows you.
These M particles gapped or not?
They're gapped.
So this either state is a Fermi liquid in that sense.
Yes, either state is a Fermi liquid.
And
I mean, I can show you more details if you want to discuss this more. But I think that this is maybe, right now it's 1 o'clock. I think this is the right moment to stop. Okay, I can put up some summary slide. And let's see if we can look here. So I can go through this. I have the slides for this here if you want. Depends on what other people are.
every system has somewhere other gapped particles. What would be good to understand is what's different here.
Yeah.
I can just excite
Yes.
some electron in the 6,000 excited level of the hydrogen
Right.
solution.
Right. The important bit is that indeed, so this flux, so you have an internal gauge symmetry in this problem. And what you're doing is you're changing your gauge by ramping the flux. Then you're absorbing this into the emergent gauge, so the internal gauge, dynamic gauge. And that's something, so it requires actually that you have an internal gauge. You need a gauge theory. Okay, so let me just briefly summarize. Yeah, so we spoke about the Toric code. I explained how to solve it. It has topological order, and one characteristic that I explained at length was the emergent anyons and the non-trivial exchange statistics. I just briefly flashed that it has implications on the ground. And then I coupled this Toric code to fermions, and again showed that you can solve the ground states. It gives some form of metallic states. Actually, there are already non-trivial metallic states I explained that there are different types of topological order and they have different sizes of Fermi surfaces. And I briefly advertised that you can use this to find blue polynomial. Okay, thank you for your attention.
Actually, have plenty of time for discussion.
I wonder whether you could go, just one, no, just for the recording.
Yeah.
I wonder whether you could go very slowly through those missed view graphs so that they're recorded.
Ah, okay, okay,
Because
send
they
you.
won't be accessible to the
Yeah. Yeah.
audience. You can do that after the talk.
Okay. Yeah.
Okay, so if you take the phone,
Yeah.
message things,
Yes.
one of the things you ramp it up.
Right. Yeah,
You'll get something that's very much like this.
it's exactly the same thing. So I didn't actually highlight it. Yeah. You end up at the Toric.
You get the Toric code and you get only on every like lattice point, square lattice.
Well, you get just the usual Toric code. Maybe it's you just get the Toric code with different. The couplings K and H are not the same. I mean, they're just different.
Yeah.
But what do you mean by they are fermions? You mean like fermions as in the second part, or like in the first part?
Well, you can think of honeycomb having like a single byte run on each vertex. And when you ramp one of the terms, you merge two sites together to give you a whole family on every site.
Right.
And then the honeycomb becomes a square.
Yes.
So it looks like there's the same thing.
It's the same thing. Yeah. It maps directly. So I should maybe say
This
this.
just seems like you want symmetry. Starting. Let's see if we get that.
Oh yes.
You switch the honeycomb.
Yeah, yeah.
So it was a superconductor to begin with.
Right.
And now what you're essentially doing when you're in terms of the fermions, what's happening is you're bringing these, you're bringing essentially the darkons, and then they gap out. That's the way that I should think of it in terms of. Anyways, but it's definitely, and actually, I think in the types honeycomb paper, it does this and maps it to. He maps it to the Toric. Yeah, yeah. So and the important bit is that essentially this is what I didn't highlight. Toric code is a quantum, is a topological quantum error correction code. It's in Z2 gauge theory, and it's actually a quantum spin liquid because it just describes this the gap part. So this triangular phase diagram. The honeycomb model describes the gap part. Three gap phases. They're all solid.
Is topological phase transition continuous, and do you know what happens to the fermion spectral function?
In our model, in this fermions. Okay, so
Do you get branch cuts at the transition point?
So we have actually within this soluble model, what we have done is we've looked at what happens. Okay, first thing, these two limiting phases are preserving all symmetries. In between, the symmetries are actually broken. Because what you have is, as I mentioned, you can have the number of flux that you want to have.
So you mean in between this one particular point?
Maybe we are speaking about different things. So let me pull up
So if you take the n equal 1/2 case, right, there is just
Is this your question?
yeah, if you just go across from the small to
So
large transition
here I'm not 100% sure whether there is something in this looks in our numerics, which is relatively coarse numerics. It looks as if there was something in between still. And here definitely there are states in between. You see the steps that you see here are just due to the numerical accuracy.
So it's more like a continuous evolution.
It's more like okay, and in this case everything is soluble, so there are just various states which are coming down in energy, step by step. But the conjecture is actually that they are going to coalesce into some form of quantum phase transition. But I cannot say whether this is really going to be a proper continuous quantum phase transition. We studied the quantum phase transition out of these states, out of this topological states. You can add some perturbations, which let ultimately some of these anions condense, and once this happens, you will get into a confining state, topological state, and you get from this topological kind of matter into a normal. And these are actually interestingly, so this side is actually a Z2 condition for star. This side actually you have a U1, you have an emergent U1 symmetry.
So there's some experimental realization of like a toric code, right? Like the school scheme.
Yes.
But then like if you add fermions to it, like do you see any way how you could realize that experimentally?
We have
the way this links to like a honeycomb model. Yeah, I mean still like it sounds like
it's very hard. We did think about an experimental realization, but you have to believe in Majorana. This one. So the Toric code, as you mentioned, here it's implemented essentially by just having some ancilla qubits which are measuring all the time and projecting all of these qubits into the corresponding plaquette eigenvalues and star eigenvalues. You can also use Majoranas. So you take topological superconductors which have fluctuating phase. Actually sort of superconductors. So you can actually create local superconducting islands, which have Majoranas at the end. At the same time, because of strong Coulomb interaction, the phase fluctuates very strongly. And there is a way of putting these together such that you create Toric code. And on that basis, you've extended this to add some more normal conducting dots in between. And suggested a way of implementing this. Well, of course, this is very far from realistic implementation, but at least there is a suggestion of how to do it.
You've made the case that there's a loophole to Lagrange's theorem based on this Toric code model, because you absorb the flux into those M particles. But you've also said that the nature of the M particle is bound to the fact that it's in 2 dimensions. Did I get that right? So does it mean that this is only a loophole in strictly 2 dimensions, or does it have implications to higher dimensions as well?
Yeah. So here it's strictly 2-dimensional, and similar arguments that I know are actually 2-dimensional. However, so the point is the exchange statistics that we discussed. For the M particles are important, and non-trivial exchange statistics in, let's say, 3 dimensions requires that you have strings or something that you can go around. Now, on the other hand, the important ingredient here is more so than the anionic nature is actually an emergent gauge theory, which allows to absorb this. So first of all, the answer is I don't know, but trying to imagine it, it's certainly hard. I guess the 2-dimensionality is important.
Can I just make a comment that we had Superior Sachdev here last time, who talked about violations of Luttinger theory as well, and his claim was that you can always do it so long as you have an emergent gauge theory.
Okay, so in 3 dimensions also.
And fractionalization.
Yeah.
He didn't say which of the two was more important or whether one led to the other. But all the examples he gave were intuitive. Good question. I don't know if anyone's seen an example. I just ask, when you say n equals a half, that's 1 fermion per 2 sites.
Sorry, so n equals a half is now, if you think of, okay, so this half of the filling allowed on the given site.
Yeah, so that's 1 fermion per site.
That's so if it's spinless fermions, then it's 1 fermion.
You have spin in your Hamiltonian.
Okay, yeah. So,
Which is what's confusing.
Exactly, yeah, you're right. Yeah.
But the spin is kind of redundant.
The spin is completely redundant, has no impact. You can do the spinless fermions equally well.
Okay.
Yeah. Or you can take also, instead of spin being only up and down, it can be 50 different types of flavors would also be.
Okay, yeah.
I did have a question.
Following on this question on like, can you kind of try to mimic the properties of the Toric code with like some sort of like a product state type of thing? Then you've mentioned that the overlap normally would be something like 1 over like n squared, like if you have the like n qubits, n squared qubits. But then like, what if you take a product state which is not in a computational basis? Let's say like in a certain basis you like fine tune to maximize that overlap. Then like, would you still get like certain, I don't know, properties of Toric code you want, or perhaps like some entanglement properties shouldn't be preserved because you catch it by a product state, or by like some, I don't know, simply like a weak perturbation away from the product state.
Yeah, if there's
Yeah, I think the question is really also what you want to know, right? What are the questions that you want to ask?
Yeah, so for instance, you might ask, well, would you still get the property that if you produce this string in a toric code, you don't need more energy than just like, you know, like 2k or like so basically the cost of like particles at the end rather than like scaling with the string size. So then like you might ask like whether you would still have that property.
You want to take the state, you want to apply a string on it, and you want to ask, you want to take the expectation value of the Hamiltonian, for example.
Yeah.
And I think that actually for this specific case, probably nothing would happen because it's just it's more a property of the string, which commutes or when you take this overlap and you have the string here and here, you can bring it across the Hamiltonian. That's essentially the main question. I think for this, for example, it wouldn't matter. But the question, of course, is whether it's whether you can call it an excitation. What does it mean? Then first, begin with, your state was not an eigenstate. When you want to apply this thing on it, it's again not an eigenstate. So what does it even mean, right? So it's so the word excitation here refers to it's an excited state, and it has a local object.
But we could also imagine creating like such Hamiltonians, which would be corresponding to that eigenstate we just created. And I'm wondering whether then, like within that class, you would get similar properties to a toric code, despite they're not like what we would conventionally call like long-range entanglement. Anyway, let's maybe just talk about that later.
There's a question from the remote audience from Gunnar, who has his hand up. I don't know if you have the sound on here.
I can try to switch. Let me see.
Gunnar?
Yes, hello. Yeah, thanks. So my question was about these kind of spontaneously formed vortex lattices in the regime where K is kind of intermediate.
On
W.
here.
Can you hear me? Yeah. Okay, sorry. I guess of course some feedback there. Yeah. Okay. Can you hear me now?
He can't hear us now. Yes, we can hear.
Great. Yeah, perfect. So the question is about the kind of spontaneously arising vortex lattices that are at intermediate value of K over W. So far you've talked about these as though the flux remains perfectly static, but is it possible that there's any fluctuations of the patterns of the flux? And another question relating to that, so can you think of this as kind of integrating out the Z2 gauge field and inducing some effective interactions for the fermions?
So first of all, then dynamic, the states that we studied, it's only a class of states, but they are all eigenstates of the Hamiltonian. So yeah, so the answer is it's not dynamic, and at the same time, then I'm wondering if I should think of them as so as far as I understand, I could indeed create in this Z2 gauge theories, I could create interactions of low-lying fermionic excitations if indeed I create there is some dynamics in it. If I'm, for example, not at this integrable limit. For example, I can imagine in this or also in the Kitai-Honeycomb model, when there are terms which are breaking integrability, these might be terms which are exciting some, let's say, boson or so. And after a while, this costs energy, so it cannot propagate forever. So it comes back, and essentially what it does for me is it creates interactions. But it doesn't happen here, I would say. Yeah. I think here really we have just so the true answer is we just studied some trial states which are symmetric with respect to the symmetry and the rotational crystalline symmetry. Of course, there are translation symmetry breaking, and again there are eigenstates.
Okay, great. Yeah, thank you.
You to put your microphone back on.
Yeah. So, first of all, your proof that you did show was basically Oshikawa's proof applied to this model.
The generalization actually to these two gauge theories is by Rami Kantin.
To show online. And my other question was, actually, we should have thought of this when we were working on this, but my question to you is, since the toric code is the large J limit of the type model, is there a correspond? Can you run that backwards and produce a TIF model, a TIF on the honeycomb model, which also has the W in it?
I see. So you want to start from here
and
want to run
backwards
backwards?
already. And it's the limit of a TIF model.
Yes.
Could I actually produce a TIF model with that W coupling or something like it, which is integral? The question I just throw out.
The answer is the answer is probably yes. The question is, what happens when you go away from the corners of this triangle? It gets, right at the corner of the triangle, probably you can do it.
I want to go right in the middle. I want to go to
Oh.
a place where I've got gapless fermions. I want to take Kitai's model and add this.
Yeah.
Is it something like this to it? Is there an integrable version like that? I mean, there's so many deformations of the Kitai model that are integrable. It seems likely that a cousin of this
Sure.
is probably.
I mean, maybe that's related to what you were doing also.
It has some overlap with it, but it's a little bit different.
Renee, question. If you turn on, do you expect the space diagram to survive up to the gap, or what happens?
Okay, so first of all, temperature and topological order by itself is a delicate question, I guess. Good, yeah. Okay, but in principle, since we have all the excitations, we can start to populate them, and as far as we are below the gap of the anyons, essentially the fermions behave just like the fermions with a given Fermi surfaces. So I think that actually, yes, I think for many aspects, even if you increase temperature, you should be able to get the same. You can ask the question, for example, about what's specific heat for this problem. And yes, it's just going to be this fermionic specific heat of the corresponding, I mean, okay, when we have a node, of course, it's for a node. And
That's what I was looking for. That's what I was asking.
Yeah, no, absolutely.
Would be even would you have one is gap with nodes, the other is gap without nodes.
Yeah.
And so we would see that in some sort of thermodynamics.
Absolutely. And indeed, I mean, up to the gap of this Toric code sector, I think you can just, you can actually directly translate from usual Fermi liquids in this case. It's actually the single particle physics in terms of correlators is special here, but the thermodynamics is going to be Fermi liquid-like.
Yeah, I think let's thank Elio for a fantastic talk again.